So there's already a typed question in the chat window that I could direct to Rodrigo. Sharon is asking him, where are the sources of damage map bridge fragility functions come from? So how do you get the bridge fragilities is the question, Rodrigo.
So regarding the ground motion information, we use OpenSSH with USERV3, and then we use the spatial correlation with Aaron Baker to account for the spatial correlation. So we generate our own ground motions. And then regarding the fragility function, we use, this builds up on the work developed by Michaela Miller in 2014 that uses the fragility functions provided by Caltrans that are mostly the ones provided by Hassens.
Thank you, Rodrigo. Any other questions? I do have a question to John about the fragilities, if I may. So John, you were showing Abacus models for doing the, I guess, the damage simulations. So when you're calculating the fragilities, are you really using the three-dimensional finite element models for each of the potential or probable displacement demands or lateral spread demands? Aren't each of those calculations like very, very kind of computationally expensive? And if you're doing like many simulations, how long does that take? Or is there a shortcut or some simplification you guys are taking?
So Abacus is being used by UC San Diego for the above ground pipes, and we are doing Abacus for the underground. The Lawrence Berkeley Lab is using a sophisticated computer program that they use for doing their analysis. But yes, when you do a full 3D analysis and you pull in all key aspects, those computations can get significant, especially for the underground system that we're looking at. I don't think as demanding for the above ground system. And so, whereas it's important to model a pipe as a shell to be able to get the correct response when you have the piping compression, you can use a 2D beam model, beam spring model. Professor O'Rourke has developed a model that's been calibrated against the experimental results at Cornell that captures many of those key aspects if the pipe is placed in the tension, which is often the case. So when you're doing a lot of analysis, we do use 2D approximations when shown to be reasonable, and then we have to do kind of a subset of analysis for the 3D cases when that's necessary. The Lawrence Berkeley Lab is doing full 3D throughout.
Thank you. I see Boris raising a hand.
Hi, hey guys, hello. Good to see you and hope that you're all in good health and good spirit. I have a question. So a lot of talk about using Monte Carlo and all these simulations. And when I talk to my mathematics colleagues, they keep saying that for each of the parameters, each of the normally distributed parameters, they would like to see at least 30 realizations. I see that people talk about 3 realizations, 4 realizations. Did somebody would it be very useful for somebody to actually put things on paper and to calculate how long will it take to come up with some of these fragilities? I've done a simple calculation for some of those regional scale models. If you take 6 hours or 10 hours to get one of those models running, and you have it, let's say just three parametric, just three components of the uncertainty, it would take 100 years. So it would be interesting for somebody to actually put on paper, to get the proper tails of distributions to see how long will actually take to get these. People talk a lot about uncertainty quantification using Monte Carlo, but it's going to take until next century to get some of those results out. So it would be very useful to actually for somebody to actually get those proper numbers of how long it takes to run and how many realizations and how many uncertain parameters, and then just spit out those numbers. Thanks.
I'm guessing, Boris, this question is directed to multiple people, but is anyone going to want to, tell some numbers about how much their calculations take? Rodrigo, you already, I think, mentioned.
So really my calculations, the simplest version of the traffic model, I mentioned that one loss curve takes 8 hours. So in that regard, to generate data to train, I use high-performance computing at Stanford. So it takes a week to generate data. But then I'm using more complex traffic models that each scenario takes around 4 hours. And then to get 1,000 data, I use the cluster for 2 weeks to get enough data to train my neural networks. So that's when it comes to my computational challenges. I don't know how the rest of the speakers deal with their computational challenges.
But if I can just interject here, so you said you use 1,000 simulations. I mean, for how many uncertain parameters? I mean, is that statistically appropriate number? I mean, if you have more than couple, more than couple parameters you're trying to model, you need many more realizations. I mean, are your tails stable, and do you get good numbers out of that? So yeah, 1,000 sounds like a lot, but statistically, statisticians will just say, no, that's not enough. That's just not good enough. I mean, you need to prove that those are good numbers, and that it takes a week. It might actually take years. So that it would be good for somebody to actually do analysis of how long will it actually get to get good numbers, good statistical numbers out of that.
As an alternative approach, what Norm Abramson and his team is doing is trying to avoid doing Monte Carlo simulations, and because of the time issue. And so we talked about polynomial chaos theory as one way that they're trying to be able to capture the forms of the models and their variances without significant loss of accuracy with a major speed up. The other thing is all of the numerical modeling that I talked about in that first response to my question. The results of that is to find the parameters that are most important. And then there's a technique called Latin hypercube sampling, where you can pick the values that you're in the space to be able to most efficiently capture the distribution, especially the tail. And the tail at low intensity levels is particularly important to be able to get robust estimates.
Yeah, thanks, John. So yeah, I know about polynomial chaos. We started using that 5-6 years ago and actually developing, and I know where the work from Norm came. Actually, there's quite a bit more to that. Polynomial chaos can also be used to develop sensitivities. This is something that I've been proposing to Pierre, but I got no luck yet. So maybe next time. Anyway, thanks.
Thanks, Boris. Any other questions? Our simulations for the bridges, for the fragility part, not the traffic part. I don't want to quote any numbers for the traffic simulations, but for the bridges, we also use a sort of a supercomputer at UCLA. I think it has 64 cores. And for us to generate the fragility curves from scratch, and our bridge parameters, we assume they're certain. So for example, their abutment soil, parameters, the stiffness and the capacity of the backfill. We use the median values reported by Caltrans, and we do not consider any variations in those parameters. So the only uncertainty we have is the ground motion itself. And so for that, we just do incremental dynamic analysis or some better, fancier version of it. And it will take about like a whole day to go analyses that did not converge and some flag was raised to see whether we are correctly classifying them.
Yeah. As a follow-up on what Professor It is saying, in terms of my model, the neural network that I'm training it's trying to replace the traffic model that in my case, given the input, is deterministic. So there is no uncertainty in the model itself that I'm using. There is uncertainty as well in the traffic model for the functions. But again, the uncertainty itself of the neural network it doesn't exist. But then the fact that we developed this neural network that takes the step that takes a long time to make really fast allows to actually perform millions of Monte Carlo simulations to account for the uncertainty of the ground motion for the functions. Like if you didn't have this this neural network, you have to run the traffic model. And as you mentioned, it will take 100 years to actually account for the uncertainty. in those parameters. But with this neural network that actually skips the deterministic phase that takes a long time to run, the Monte Carlo analysis can be performed now.
I see my internet connection is a little bit unstable, but hopefully you guys are able to hear me without too much disruption. Any other questions? I do not see from the chat window, but anyone has any live questions? All right, I think then we can go to our break. I'd like to thank all the speakers for the work they presented. They're all very interesting. So I guess we're ready to take a break.